It's time to start, everybody, but I only got two of you in here, so feel free to ask me any questions you have. I'm gonna have to start up in a second, at least for you two guys. See if my computer's up yet. My iPad, anyways.
Is there going to be a practice test for the final that like has all the chapters combined?
Yeah, I have one that I can just put out there. It's just the problem is I cut everything so short in chapters 27, 28, 29, that it doesn't fit that very well. So I'm gonna have to remake it. The closest thing right now is really just doing the retest or the practice test for all the previous ones. But yeah, I'm definitely going to if it's not done tonight, it'll be done first thing tomorrow. So we'll have it up.
Okay, and then do we have to do the chapter 30 homework?
No, that is an extra credit. Basically, the only thing you have to do for credit is chapters 17 through 29. Everything else is extra credit. Any other questions, anyone? All right, I guess I should just go ahead and get started then. Maybe the rest of the people will watch the video, but these are the critical things. You should notice that I did put some specific videos up on from my YouTube channel. Those are actually showing all the things that I'm talking about now and more stuff. What times are we allowed to take the final exam? Yes. If you wish to take the final exam with me, I'm going to put this out to everyone instead of just to respond to the person asked. If you are taking the exam, the final exam with me in Virginia Beach, then you can take it. I'm typing this up so you'll have it in writing, but I'm also saying it out loud so you'll have it on the video. So if you're taking the final exam with me in Virginia Beach, then you can take it uh, at 9 a.m., 10 a.m., 11 a.m., 12 p.m., or 1 p.m. on Monday, Tuesday, or Wednesday. So basically next week you can take it on the Monday. Your day is supposed to be Tuesday at 2:15, and your lab teacher has told me that she will be there for you guys to take it at that time. I think your class starts at 2:15. So anyways, you can do it then at Tuesday at 2:15 p.m. That's what everybody's expecting, but you're perfectly welcome to come take it on Monday or Tuesday or Wednesday with me in JC 21 or JC 26. In other words, I have access to both of those rooms. If I have so many people that I need more computers than I have in one room, then I'll use the other one. But generally speaking, I'll be in one of those lab rooms to proctor it for you. Anything else?
That's at Virginia Beach campus, correct?
Yeah, but the Miss Raskovic, she's willing to do it at the Chesapeake campus at 12 at 2:15, whatever your normal lab time is. I'm pretty confident she told me it was 2:15. So if that's not your normal lab time, that is what she told me. So you might want to confer with her if that's different from the regular time.
Okay.
All right. I actually had two people took it today. And one person came yesterday to take it, but I didn't have it ready good enough, so they came back again today. So some people have already taken it. Uh, that because of that, I've had to make multiple versions because students, I don't want any possibility of a student seeing exam questions, say on Thursday or Wednesday, and then letting people know, and then Monday, Tuesday, or Wednesday, someone takes it and has a slight advantage. So the questions change from that version to the versions that we have on Monday, and a different version on Tuesday, and a different version on Wednesday. Anything else? All
Could you
right.
put an announcement when you make the practice final available?
Yeah, I'll send out an email to everybody. I don't mind doing that at all. Man, I had my Windows has been, or my Zoom has been updated, and wow, I don't know anything about anything now. Let's see. Documents, nope, advanced, computer up. There he goes. Okay. They even moved the place where I had to click the button to share my iPad. Whew, that was scary for a second there. I didn't know where I was going. Okay, it should come up now. Okay, I just did mirroring by mistake. That was not what I was supposed to do. Hold on, something else is happening. This is weird. Let's see what it does now. Hold on. Huh. Something happened with my share screen, and I'm not sure why it did that. Let's see what I can do now. Try again now. Okay, it looks like it might be working now. Whew, that was scary. Didn't know what was going on. All right, now you can see it. So, any more questions before we get cracking? Okay. Well, what we did last time was we went over the law of abuse of art. My intent was to go over abuse of art, but I'd spent so much time making sure I reviewed what we had gone over in the magnetism chapter, which was the previous chapter. I think it was 20, excuse me, I think it was chapter 27. But like I said, since I went over so much time on that, I ended up only having enough time to go over the law of abuse of art, but I at least was able to do that. And I've put more links to more videos where I'm showing you how to use Bios of Art and where I'm showing you how to use Ampere's law. So now what I'm going to do is show you the paradigm that happens with regards to Ampere's law, because this thing I call a paradigm, it's actually a three-step process. Just like this three-step process you had for Gauss's law, where you take Gauss's law, in principle, you could have used Coulomb's law as well. But the main thing is you're either using an integral form of Coulomb's law, or you're using Gauss's law in integral form, and you're using that to determine an electric field. Once you have the electric field, then you're supposed to use the change in voltage is equal to the negative integral of E dot dl to determine the voltage difference between the negative plate and the positive plate in a capacitor. Now, that could be a parallel plate capacitor, in which case saying plate makes perfectly good sense, but it can also be in a coaxial cable, where instead of two plates, you have a coaxial cylinder and a coaxial cylinder shell, and one of them is going to be positive, the other one's going to be negative, and you're going to calculate the voltage between the negative one and the positive one so that you get a positive quantity. And of course, if you have a sphere inside of a sphere, you can do the same thing as well. So all of those would require you to use Gauss's law to find the electric field. In the case of a parallel plate capacitor, it'd be above and below a plate that has a uniform charge density of sigma, say. And you know that when we do that for a plate, we get sigma over 2 epsilon naught. And then we take two plates and put them next to each other, one positive, one negative. And and we put them close together. And it turns out that when you do that, the positive plate will create an electric field pointing, let's say, to the right, and then the negative plate to its right will create a electric field pointing to the right as well. So you end up getting sigma over 2 epsilon naught plus sigma over 2 epsilon naught gives you sigma over epsilon naught. That's the whole field in between the two plates. Then you integrate from the negative plate to the positive plate, get a voltage that turns out to be E times L. Again, using delta V equals the negative integral of E dot dl, you get E times L or E times D, where L or D is the separation between the plates. And then after that, you use C equals Q over V to calculate the capacitance. If you did it with a coaxial cable, you're going to calculate the electric field between the inner tube, the inner cylindrical wire, and the outer cylindrical shell, coaxial, of course. And that electric field between them can then be used in V equals the negative integral of E dot dl to calculate the voltage difference between the negative one and the positive one. And then you can again use C equals Q over V to calculate the capacitance for a coaxial cable. It's normally done in terms of capacitance per unit length, but the main thing is you need to be able to do that paradigm. And then the third version for the Gaussian paradigm is again using Gauss's law to find the electric field between the inner charged sphere and the outer charged spherical shell. Then use V equals the negative integral of E dot dl to integrate between the negative sphere and the positive sphere to get the voltage. Then you use C equals Q over V to find the capacitance. So that's the three different types of problems you got to be able to do for Gauss's law. Now in this one, we're going to use Ampere's law. In principle, again, you could use the law of Biot-Savart, but either way, you're going to do an integral or use an integral equation to compute the magnetic field. In one case, it'd be the magnetic field of, for instance, a solenoid. And once you get the magnetic field for the magnetic field inside of the solenoid, then you can use the definition of flux, which is the integral of B dot dA, to calculate the flux through the end of the solenoid. And then you're going to use L equals N times the flux over I to calculate the self-inductance. So that'd give you the self-inductance of a solenoid. You can then use also for a torus, which is basically a solenoid. You imagine a solenoid is like a coil of wires, very neatly packed, but goes on for some distance with a little cross-sectional area like that on each end. And that's the area over which the flux is. Now, if you take that really long one and imagine turning it around till it makes a donut, then you have what's called a torus, T-O-R-U-S. With the torus, you can again use Gauss's law or Ampere's law. Shoot, I can't stop yawning. So you again use Ampere's law or the law of Biot-Savart to calculate the electric field inside of the donut. Okay. Once you have that magnetic field, I think I said electric field a second ago, but once you have that magnetic field inside of the torus, then you can use the definition of magnetic flux, which is the integral of B dot dA, to find the flux through the little cross section of the donut. So remember, the donut would be all this, and then that little cross section is the area through which the magnetic field fluxes. So you take and calculate that flux, and then you use L equals N, the number of turns times the flux divided by the current, to calculate the self-inductance of the torus. And then finally, you can do it again with a coaxial cable, just like we did with the coaxial cable in calculating the capacitance, but this time we're going to calculate the inductance or the self-inductance of the coaxial cable. So you'd use Ampere's law to compute the strength of the magnetic field, again, between the inner cylinder, which maybe carries a current in to the left, and then between that current and the outer cylindrical shell, you're going to calculate the magnetic flux, which is the integral of B dot dA. And this time it's over a little rectangular area that starts at radius R1 and ends at radius R2. And then going through that little rectangular area over a length L, that will give you the magnetic flux through a length L of coaxial cable. Then you take in the number of turns. That's just one in this case, whereas the solenoid and the torus have very distinct numbers for n. But in this case, it's just n equal 1. But you take that flux and divide it by the current, and that'll give you the self-inductance. So I'm going to show you that last bit, 3 bits. So hopefully that explanation helps you understand what we're shooting for. Did someone try to say something a second ago? Guess not. I thought I heard something, but it might have been TV. All right. So now I got to turn the chat on too, because I keep forgetting to do that. Yes, no one else chatted anything. All right, the chat window's open. So what I want to let you guys know, I haven't even really given you much of an introduction to Ampere's law. So let's just start off out of the box saying what Ampere's law is. So remember Gauss's law said the closed integral of E dot dA is equal to Q enclosed over epsilon naught, and that was really a nice helpful thing. But what we did is we learned that using this integral equation, we can extract the integrand out of the equation if it has certain symmetries. The symmetries had to be, of course, infinitely long and infinitely wide planar, or a infinitely long cylinder, or a sphere. If you don't have one of those 3 symmetries, you can't use Gauss's law, period. But because of those symmetries, that allowed us to always evaluate the left-hand side to be sometimes more than one term, but the terms that weren't 0 were always just an electric field times an area. Okay, in some cases, it became 2 terms that were electric field times an area, or electric field, well, yeah, just electric field times an area, and then the other ones would be 0. Sometimes the Gaussian surface was a soup can where only the top and bottom gave non-zero left-hand sides, but other times it was a soup can where only the soup can's label side had a non-zero integral. And then the third operation was when we used a spherical Gaussian surface. So in here, we're going to have either a solenoid symmetry, which we sort of imagine as if it's infinitely long, but not really. And then there could be a torus symmetry, and then there could be a coaxial cable. And that one, we were definitely thinking of it as infinitely long. So that's the equation for Gauss's law. The equation for Ampere's law is the closed integral of B dot dl. Notice this is a line integral, not a surface integral like Gauss's law was. Okay, Gauss's law was a integral over a surface. This one's an integral over a closed loop. It's got the circle on the integral. That means it's something closed. In this case, it has to be a closed loop. So you can imagine a little line or path that you follow. As long as the line starts in one place and ends up back at that place, then that's a fair assessment. So the left-hand side is the integral of B dot dl, but the right-hand side is mu 0 times I enclosed. And there's a right-hand rule associated with this, such that if you put your right-hand fingers to curl around the path in such a way that they're curling the same way that you're integrating around the path, then the current enclosed is any current that pierces a surface that could be bounded by that curve. That's going to be a little bit more complicated, and that's going to bring up some important stuff later. So I wanted you to understand that if you had, for instance, a path like that, that's perfectly fine. But what matters is the path has got to go around either this way, which looks like it's counterclockwise, or it's got to go the other way, in which case it'd be a clockwise. Now, what you want to say is that boundary, that path is a boundary for a surface. So what I tell my students is imagine making that path out of, say, a coat hanger. So you take the metal of a coat hanger and you straighten it out really long, using a lot of effort, and then you bend it into exactly the shape. Now you take that coat hanger and you dip it into, let's say, a paint tray that's filled with water and a solution of glycerin and dish detergent soap. So it's mostly water, but there's some soap and some glycerin in it. That'll make it a little bit thicker. You mix that solution up, and it's basically the same stuff that you used to use as a kid to stick a little ring in and blow bubbles, right? So if you took this ring and you laid it in that bubble solution and then pulled it out, you would basically get a bubble surface. In other words, it's not a bubble yet, but it's the same material that the bubble would be made of. And that surface would be essentially flat like this. Okay. Well, that surface is in fact bound by this curve. So that surface is acceptable. But if you now took that loop and pulled it like you did when you were a kid with the actual bubbles, you would make a big bubble out of it. And until it let go, it wouldn't be a complete closed bubble. It would just be like a sack of various odd shapes. Well, every one of those various odd shapes that you can make that has a boundary as this blue curve, every current that penetrates one of those shapes is acceptable to use as ion closed. And in this case, since it's going counterclockwise, I hold my right hand over it and curl my fingers in a counterclockwise direction, and I see that my thumb points perpendicularly up from that bubble surface. So any current coming from the bottom, piercing through the top, going that way, will be considered a positive current. Any current going the other way will be considered a negative current. And that's important. You got to keep track of that. Okay. So that's the kind of contour that we're integrating over, and it has a right-hand rule associated with it. So I'll just write that here, right-hand rule. So if we in fact had a current that went like this, and notice I'm saying this is exactly perpendicular to that surface, and it's exactly perpendicular there. This would be a positive current. If, on the other hand, we had, I think this will write. That did not turn out to be a color that was a good idea. I'm going to change it to this slightly different color. This would be a negative current. And now it looks like ketchup and tomato and mustard. Okay, so that's the key part that you have to understand. And of course, just like we had Q enclosed could be equal to an integral of lambda dl, or an integral of sigma dA, or an integral of rho dV. We also have that I enclosed could be equal to an integral of J dot dA, where J is the current density. There actually happens to be a surface version of that too, but only a surface version and a cross-sectional version like we have here. The surface version is K, and it would be dot D, DL sort of to some extent. So if you had a surface charge as opposed to a surface density of current flowing on the outside surface, that's another case. So anyways, that comes into play. But those are the only two options, and we generally never use the bottom one, the K, so you can ignore that until you get to a more advanced class. So let me show you how we're going to use it. For instance, we've done with the Biot-Savart last time, we worked a infinitely long wire aligned along the z-axis. So I'm going to do the exact same thing now. I'm going to do an infinitely long wire aligned along the z-axis, and I'm going to use Ampere's law to compute what the magnetic field is. So I'm going to say Z is right here. I'm going to say X is, actually I'll say Y is right there. And then I'll say X is coming out of the page like that. Now what I'm going to do is draw the wire like that. And now I'm going to try to draw the wire over here as well. Okay, so that's our wire. And this, for instance, is the top of the wire. That's the bottom of the wire. And in fact, this wire goes on for infinity that way and for infinity that way. And what I'm going to say is there is a current I going upward. What we would like to know is if I go a distance, let's say R out here, what would be the magnetic field at that point? So now what I'm going to do is put a little spot here in green and say, this is what I'm calling a point. So this is the point at which we wish to know B. In other words, we're wanting to know the magnetic field at that point. Now, I've already taught you about a right-hand rule. So if you imagine this is the wire and the fact that a point is pointing up tells you the current is going up, then you're going to take your right hand and point your right thumb in the same direction as the current and your fingers wrap around it. Now, if you look at this, you can see that that's in a counterclockwise direction. So what that means is if you come out here in front of, let's say in front of the wire, which would be right here, the magnetic field is going to point to the right. If you go back here to the right of the wire, it's going to point into the page. If you, let's do this real quick. I'm going to change it back to black. I want to continue the x-axis back here like this. So if I now go back behind the wire, the magnetic field would point to the left. And if I want to go back to this again, this is the negative y-axis. So if I come to the left of the wire, we would expect it coming out of the page. Okay. So, and of course, in between, like right here, it would go that way, say, and right here, it would go that way, say. The main thing is it just makes on a particular circle whose center is centered on the middle of the wire, you can choose any circle around the wire perpendicular to the wire. And on that circle, the magnetic field, as long as it's centered on the wire, will be a constant magnitude everywhere on that circle. What we're going to calculate is what the poop is that magnitude. Okay. So that's what we're trying to figure out. If you'll notice, though, one of the things you have studied in the past in trigonometry, hopefully, was your polar coordinates. So you could have, instead of x and y, you can have the polar coordinates r and theta, where r is the square root of x squared plus y squared, and theta is the, well, you could call it the inverse cosine of x over r, or you could call it the inverse sine of y over r, or you call it the inverse tangent of y over x. So in all those cases, that's the angle theta. And if you imagined a line perpendicular to a radial line, but pointing in the direction of increasing theta, that is a vector that exists in reality. It's one that we've defined, and it's called theta hat. Whereas the line that comes from the origin to a particular point in the xy plane is also related to a vector. That is a radial distance. And if you imagined a vector parallel to that, whose length was 1 unit long, that would be the r hat vector. And of course, the one that I just mentioned was the theta hat vector. That would be a unit vector as well. So knowing that they exist will make our life a little easier. What I need to explain about this, though, is notice the symmetry of a circular wire tells us that we could have arbitrarily put that x-axis anywhere. We didn't have to have it coming out of the page. We could have had it coming out of the page, but 15 degrees to that side. And then, of course, 90 degrees ahead of that would be the y-axis. So the y-axis would be 15 degrees tilted behind the page. And then the negative x-axis would be basically another 90 degrees from that. And then the negative y-axis would be another 90 degrees from that. But you can rotate it by any angle and always be there. So even though this into the page appears to be in the negative I hat direction, it's actually the same as the theta hat direction. So I'll say, but actually, by symmetry, it is the theta hat direction. So that's a more complete way of saying it. And once you understand what the theta hat direction is, it makes a lot more sense to call it the theta hat direction. If I drew it just in, let me draw it down here, at least briefly, to show you what I mean. So I'm going to draw, this will be my x-axis. So we're forgetting about the z-axis for just a while. So this will be my y-axis. That'll be my x-axis right there. If you imagine a particular point in space, that point in space would be obviously x comma y, where that's my x, and this would be my y, but it's also r theta. And this distance would be r, so you can see r is equal to the square root of x squared plus y squared. But our angle theta would be this angle. Okay. Now, what I'm saying about these vectors is right here. Let me redo that. That's not so good. And I'm going to zoom in on it so you can see it. So right here, we're looking at the XY axis, and the Z axis, of course, would be coming out of the page towards us. But what I'm going to say is there's a unit vector right here that's 1 unit long. Notice it points radially outward. That is our R hat vector. And then there's also a vector which is perpendicular to the R hat vector, and that vector is the theta hat vector. It's normal that we'd actually write the vectors right here as R hat and theta hat. If you look at this, you can probably convince yourself that R hat is actually cosine theta I hat plus plus sine theta j hat. And then you can also figure out that theta hat would be negative sine theta I hat plus cosine theta j hat. So that's really what those vectors are. It might even help you to realize that dr hat over d theta is actually equal to theta hat. So that way, if you ever forget it, you can know, well, at least I just take a derivative and I'll get the theta hat. So now you see what I mean. If the r vector was parallel to the x-axis, then clearly the theta hat would point in the j hat direction. If, however, r hat vector was along the y-axis and therefore the r was along the y-axis, then theta hat would point to the left, and that would be in the negative I hat direction, which is exactly what we look like up here. So into the page was the negative I hat direction, but that's just because that's one particular point in space. But by symmetry, I could make any direction the y direction and any direction the x direction and still keep the z axis along the wire. So that's what tells us that really our hypothesis, remember how I used to do a hypothesis for Gauss's law? We're going to do a hypothesis for this as well. So hypothesis about the magnetic field is B, the magnetic field might depend on the radial distance r, in other words, the perpendicular distance from the center of the wire to whatever point you are in space, and it's going to point in the theta hat direction. That's my hypothesis. So now, just like I did with Gauss's law, I'm going to write left-hand side. Okay. And I'm going to write left-hand side, and I'm going to draw my Amperian loop. And let's say I put my Amperian loop in the color of purple. So my Amperian loop here is going to be basically this circle right here. That's supposed to be a circle. It doesn't look very much like a circle because it got kind of narrow on that, but I think that's pretty good right there. So that's the Amperian loop. Just like we had a Gaussian surface, now we have an Amperian loop. And what I'm going to do is I'm going to, for starters, make sure y'all see that's back behind. So I'll just do that. And then I'll pull out the blue and fix that. And then I'll pull out the black and fix that. And then I'll pull out the blue again and fix that. So now you see that oval that's really just a circle being represented by an oval. You can see that is out a distance r, because it obviously goes right through that point r. And that's our Amperian loop. So I'm going to say arrow Amperian loop. So that's the Amperian loop, and consistent with the right-hand rule, I'm going to integrate around that in the counterclockwise direction as seen from above, which is going to, in fact, allow this current that we have to be in the positive direction according to that right-hand rule I told you about. So now I can just write the left-hand side is the integral of b dot dl. But now I'm going to put in my hypothesis, and my hypothesis is that it's going to be B that possibly is related to R. From symmetry, I see it definitely can't depend on Z. It can't really depend on X by itself or Y by itself. So really R is the only fair thing. And then it points in the theta hat direction. And then my DL, notice we're going along a circle of radius R. So some little length of it, you can imagine, would be like this. This would be my angle theta. And then you allow theta to change a little bit by an amount d theta. And then this little segment right here would be what I call my DL. So that's the little DL I'm talking about. Notice it points, it's tangential to the circle, but it points in the same direction as we're going around the circle. And therefore, it, from S equals R times theta, we know this is going to be R times d theta, but it too is pointing in the theta hat direction. So now I can put down my DL as R d theta, theta hat. And this is all over the Amperian loop, which has a radius r. So that immediately tells us that B of r is a constant, and r itself is a constant that can be pulled out from the integral. And the dot product's a linear operator, so I can really just pull all that stuff out in front and leave theta hat dot theta hat on the end. And all I'm left with now is d theta times theta hat dotted with theta hat. But remember, dot products can also be computed by taking the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them, which is 0 degrees. So you see that theta hat dot theta hat just becomes 1, but the integral d theta goes from theta equals 0 to 2 pi radians. So we ultimately get that the left-hand side is 2 pi r b of r. Everybody follow how that left-hand side became b of r times 2 pi r? Anybody have any questions? Now I'm going to say right-hand side is mu 0 I enclosed. Now the total current enclosed is just I, and it happens to be consistent with my right-hand rule. So I'm just going to say it's mu 0 times positive I, which is just mu 0 I. Now I'll set left-hand side equal to right-hand side, and that gives me 2 pi r b of r is equal to mu 0 I. Therefore, we have, consistent with our hypothesis, mu 0 I over 2 pi r theta hat is the magnetic field that we already knew the formula for, but now we've used Ampere's law to show it. Okay. So that's how we use Ampere's law to calculate a magnetic field. Specifically, in this case, it's for an infinitely long wire. Okay. Again, in the physics world, infinitely long means if you're 10 centimeters away from the wire, then you'd hope you're at least 100 centimeters away from either end. Of course, that's only a factor of 10, so a factor of 100 would be even better. So if it's 10 meters away from each end, then you're even more sure. And if it's bigger than that, you're even more sure still. Okay. And that also, that using of Ampere's law is the first step of the what I'm calling a paradigm. So this is the first step in the paradigm. Okay. The second step is using phi, the magnetic flux, is equal to the integral of b dot dA to find the flux. And then the third step is using L is equal to N times theta B over I, where this L is called the self inductance. Actually, I can't write it that small without looking really crappy. So it's the self inductance. But most people leave the word self off. And by the way, it has units of henries. Okay, so that's the process we're supposed to go through now that we have some idea about the Amperian loop and Ampere's law and how to apply it. So let me try another example so you can get a better feel for how to do Ampere's law. Let's imagine this time I'm going to take the same symmetry just because we just finished doing it, so hopefully it'll be helpful. I really should have used that with my little tool, so now I'm going to do it with my tool. Okay, and then I'm going to do right here is my x-axis is right here. So this is x, this is y, and this is z. I'm going to draw my wire again like an infinitely long wire. And this time I'm going to actually make it somewhat finite in radius. Okay. It goes on again for infinity that way and for infinity that way. And I'm going to say the radius is just plain A. But in addition to that, I'm going to say that there is a outer shell that is a concentric cylindrical shell. And from that, we can say that is our circle, and this guy has a radius of B. Okay, and in fact, it could be infinitely thin, which is fine, but I'm going to try to make it like a physical object. So I'll draw it like this. I'll draw this like this, draw this like this. Oh, that did not turn out good. This will be like this. And this will be like that. Okay. So now what I have is a coaxial wire. And I'm going to say I is going that way, but there's also a current I going this way in the outer part. And it's just air in between. Okay. Everybody understand that drawing, what that is? Anybody have any questions? Okay. This is a coaxial cable. And I'll say this, for instance, is a radius C, but that one's not going to come into play at all. B is the radius to the inside of the cylindrical shell, and A is the radius of the inner wire. So this is a, whoa, I don't know what happened with my word cable there, but anyways, this is a coaxial cable with a current I uniformly distributed over the cross-sectional areas of the inner and outer cylinder. Now, obviously, the outer cylinder is a cylindrical shell. The inner cylinder is just a cylinder, but I just wanted to make sure that's clear. But the uniformly distributed tells us that basically uniformly distributed implies that J is equal to a constant. Remember, J is our current per unit area. That means I over pi a squared is the J for the inner circle, and I over pi c squared minus b squared is the current density. Actually, I shouldn't say those two are equal, but J outer is equal to I over pi c squared minus b squared. That's what it means to have them uniformly distributed, meaning you can just take the I and divide it by the cross-sectional area of the wire geometrically, and that'll give you J. Okay. What I want to do is find B for R less than A. Let's say A less than R less than B, and then B less than R less than C, and R greater than C. Okay. So first off, I'm going to imagine zooming in here, and now I'm going to choose an Amperian loop. I'm going to use a purple Amperian loop. And I'm going around like that. And of course, I'm going to go in the counterclockwise way so that that current will be upwards. So everybody see what that is right there? See how I'm going in that little loop? That loop is perpendicular to the wire. It's centered on the center of the wire, and it's completely inside, and its radius is r. So I should say that distance is r. Okay. Now I had to zoom in to show you that, but you should have an idea roughly what we're talking about here because we just finished doing the same thing before, only we had an Amperian loop that was bigger than the radius A. In this case, it's smaller. So I'm going to start off with my solution. I'm going to work like this. Closed integral b dot dl is equal to mu 0 I enclosed. And I'm going to say my hypothesis is the same thing. It's going to be B is equal to B of R theta hat. And now I'm going to address this problem for R less than A. Left-hand side. Now, this is the point where you're supposed to realize, hey, we choose an Amperian loop and a very specific Amperian loop so that the dot product turns out to be, for this whole thing, the whole integral is going to force the dot product in the integral to become b times some length. We know exactly what that is. I'm going to say the integral of b of r theta hat dotted with r d theta theta hat, which is going to become b of r times the integral d theta times theta hat dot theta hat, which of course is 1. So we're going to get basically equal to 2 pi r b of r. Now, every time you do a coaxial cable, that's going to be the left-hand side. Period. No ifs, ands, or buts about it. Okay. So you always get that. The right-hand side, this is the part where sometimes you might have to actually integrate, is when you're doing the right-hand side. You're technically fulfilling an integral by doing the left-hand side, but you're completely avoiding it by a really smart choice of the contour that you're using. So the right-hand side is mu 0 I enclosed. Notice that the I is pointing in the exact right direction for the right-hand rule, so I know it's going to be positive. But here's the thing. J equals a constant, which is equal to pi over pi a, or excuse me, I over pi a squared. But that means I enclosed over pi r squared is equal to that because it has to be a constant. So for any section that you took, in this case, it's a circular section whose radius is r instead of a. From that, we can get I enclosed is just going to be equal to r squared over a squared. Need to make that a little bigger so y'all can see it. So it's r squared over a squared times the total current. So you can see, since r is less than a, this is clearly going to be a fraction of the total current, which is what we expect. So now I can say this is equal to mu 0 r squared I over a squared. Now we say left-hand side equals right-hand side. And when we do that, we get 2 pi r b of r is equal to mu 0 r squared I over a squared. You can see that the r squared is going to cancel out with the r over here, leaving just an r in the other side. And now we have b is equal to mu 0 r I over 2 pi a squared, and that is in the theta hat direction, and this is for r less than a. So notice all the units still work out because it's just like mu 0 I over r, but this time I have the r in the top. Oops. This time I have the r in the top and the a squared's in the bottom. So that a squared in the bottom cancels out the extra unit of r on top so that it still looks like mu 0 I over 2 pi over distance squared. Okay. So now I'm going to do another Amperian loop. This time I'm going to do it for r in between a and b. So let me pull out my purple. I've got my purple out now and my purple color. Now I'm going to say this is my Amperian loop. And of course it has a radius r again. And notice I'm integrating again in a counterclockwise direction so that the current going through it is a positive current. So now I'll say A is less than R is less than B. Left-hand side is going to be closed integral B dot dl, and that's just equal to 2 pi r b of r. And the right-hand side is even easier. This is going to be mu 0 I enclosed, but this time the total current from the inner wire is enclosed. So all I have to do is write mu 0 I. So now I'm going to get, sitting left-hand side equal to right-hand side, I'm going to get the exact same thing I had in the previous example. So it's going to be mu 0 I over 2 pi r theta hat for a less than r less than b. And you'll notice that if I substitute a equal to r, I get the same thing. So I can now add this equal to part to it. Does that make sense to everyone? Now I have to do b is less than r is less than c. And my left-hand side is going to be the closed integral b dot dl, which is 2 pi r b of r again. My right-hand side is going to equal mu 0 I enclosed. But this time, remember, the equation for j is I over pi c squared minus b squared. So I'm going to say I over pi c squared minus b squared is equal to I enclosed over, this time it's going to be pi r squared minus b squared, because that's the area from B out to the point R. Ooh, we're not, yeah, this is the out to the point R. I just didn't draw my Amperian loop yet. So let me go ahead and draw that so there's no confusion. Whoa, Nelly, that's not the right color. So my Amperian loop is actually out here. Oops. Like that. Again, I'm integrating around in a counterclockwise direction. But notice this time the current inside is in the positive direction, but the current on the inside of the B to C part, that's actually in the negative direction. So that's going to be a bit of a problem. But either way, we've got the I enclosed part. Oops. So from this, I've got I enclosed, And I'm just talking, according to the densities, I'm just talking about the part of the current that is in the outer shell. There's still the current from the middle wire that I have to take into account. So I will do that by saying I enclosed is equal to, I gotta do it differently. Hold on. Is equal to c squared minus b squared over r squared minus b squared times, did I do that right? Nope, I did it upside down. Got to watch out with your math here. It's really easy to make a careless mistake. So this is going to be r squared minus b squared over c squared minus b squared, and then but that one, notice we're integrating around in a counterclockwise direction. So the current is going to be a negative for that one. And then I still have the other current as just plus I. Now I could get a common denominator for that. And if I did so, it would look like this. I'm going to say negative r squared plus b squared, that's for the first term. And then I'm going to get a denominator of c squared minus b squared. So this is going to be plus c squared minus b squared. All that will be over c squared minus b squared. And we have a common factor of I now. So I could just write it like that. But you can see that the b squareds, one's positive. Oh, darn it. One is positive and one is negative, so that's going to be okay. So I'm actually going to get c squared minus r squared over c squared minus b squared. So now I can write this part is just, oops, write it in red. This part is just mu 0 I times c squared minus r squared over c squared minus b squared. So if I set the left-hand side equal to right-hand side, I get something that's not quite as pretty as it used to be. 2 pi r times b of r is equal to mu 0 I over, well, actually, I'll just say it like this. Mu 0 I times c squared minus r squared over c squared minus b squared, like that. So now I can say B is equal to, really, really complicated scenario here, but it's going to be mu 0 I over 2 pi r c squared minus r squared over c squared minus b squared in the theta hat direction. And this is for B is less than R is less than C. If you now look at R equals B, you can see you get c squared minus b squared over c squared minus b squared. So that whole factor there becomes 1. And that tells us now that I can put a bar there and a bar there, because equal to means it's continuous across the boundary. Oops. Okay. Now I can finally do the last part, which is R greater than C. And I can say the left-hand side is equal to the integral b dot dl, but that's just going to be 2 pi r b of r. Now here's the cool part. The right-hand side is going to be mu 0 I enclosed, but notice the total current once I make an Amperian loop outside, which would be like this, Oops. Okay, I'm going around this direction again. So you see, by going around this direction, the inner current is positive and the outer current is negative, but they're equal in magnitude, so I just get 0. So lo and behold, B is equal to 0 for R greater than C. Okay. And this actually does line up basically to that. If you put in R equals C, you get C squared minus C squared in the numerator, and that gives you 0. So now I can put a underbar to show that it's greater than R equal to. And now I have the magnetic field for all the locations. Any questions on that one? Okay, now that I've done 2 of these Gauss's law types problems, I'm going to go ahead and show you the full paradigm really quickly. So let's draw another coordinate system. I don't have to make it quite as big and nice as the last one because we learned what we needed to learn on those last 2 examples. There's our x-axis, there's our y-axis, there's our z-axis. Again, I am going to imagine a wire that's infinitely long. And evidently this is going to make me redraw this several times. Dang it. And then we're actually going to have an outer one here because I'm doing a coaxial cable. And the other side of the outer one is here. And now what I'm going to do is say this is like that, and this is like that. This is like that. This is like that. This goes on forever that way. This goes on forever that way. I have a current inside of that I going downward. I have a current inside of this going upward. And we want to know for here, since I'm actually calculating the self-inductance, I need to make my Amperian loop just in between because I need to know the magnetic field between the 2 conductors. So again, I'm integrating around this way. And this right here is a distance R. So my question is, find the self-inductance Okay, that's the whole problem. I'm going to say solution. The equations I need are the closed integral b dot dl is equal to mu 0 I enclosed. I need my flux, the magnetic flux phi sub b is equal to the integral of b dot dA. And I need that L, the self-inductance, is equal to n, the number of turns, times phi b, which is the magnetic flux, divided by I, the current. And this is going to be 1, and this is self-inductance, also called inductance. Now I'm also going to say that I need the following, which is a hypothesis. B is equal to some B of R theta hat. So now I'm going to say left-hand side. B dot dl is equal to integral B of r theta hat dot r d theta theta hat, which gives me 2 pi r times B of r. Right hand side is going to be equal to mu 0 I enclosed, which is, of course, mu 0 times I. So left-hand side equals right-hand side, gives me B is equal to mu 0 I over 2 pi r in the theta hat direction, and that's for A less than R less than B, which, using some stuff from the previous diagram, that A and B should make some sense to you. So I've got the magnetic field. Now I want to calculate the flux. Now the flux that's relevant here is actually going to be, let's do a different color. I've got blue, purple, and red all drawn here. Let's do a green. Whoa, Nelly. So I'm going to do green. And what I'm going to imagine is a little rectangular box that goes this way. I'm going to say the length of this box is L. And then, of course, this distance from here to here is really, that's technically B minus A. Okay. But my differential area element is going to be this little shape right here, because I see that the magnetic field depends on the distance r you are away. So what I'm choosing is a differential element whose dimension is only infinitesimally different from r from one side to the other. In other words, it goes from r, which is the inside edge, to r plus dr. So that means this little box right here gives me dA is going to be L times dr, and then the vector is actually going to point in the theta hat direction. So now I can say the magnetic flux, going back to my purple, now I can say the magnetic flux phi sub B is the integral of B dot dA. Well, that's going to be the integral of mu 0 I over 2 pi r theta hat, and then that's dotted with L times R, or excuse me, L times dr in the theta hat direction as well. That's going to allow me to pull out the mu 0, the I, the 2 pi, and the L. All of those are constants, and now I've got the integral of dr over r times theta hat dot theta hat, which again is just 1. And of course, I'm going to integrate it from r equals A to r equals B. So I just basically get, I'm not going to write it there, it's too small a space. That's going to give me mu 0 I L over 2 pi times the natural log of B over A, because the integral of dr over r is the natural log. The natural log evaluated at B is ln B. The natural log evaluated at A is ln A. So I get ln B minus ln A, and the rule of logarithms tells us that ln of B minus the ln of A is the same thing as ln of B over A. So that's what that is. Now I have the flux. This was step 2. So this was step 1 of the paradigm. And now I'm going to step 2, step 3. Now I'm going to use L is equal to N times phi B over I. We already said the n is equal to 1, so therefore I'm going to say L is just equal to mu 0 I L over 2 pi ln B over A. All that's going to be divided by I. So you can see that this I is going to cancel out with that I. And we normally, when we're talking about coaxial cables, we normally talk about the inductance per unit length or the capacitance per unit length. So I'm going to divide both sides by L. And what will come out of this is that oops, wrong color. What's going to come from this is the inductance per unit length is equal to mu 0 natural log B over A divided by 2 pi. Notice it only depends on geometry. There shouldn't be any currents in there. There shouldn't be any J's or lambdas or rhos or sigmas. Uh, it's only a geometric quantity, and this is called the inductance per unit length. And that's the total answer. So that three-step process right there is what I've been telling you guys is an absolute essential, something you have to be able to do. Just like the paradigm I showed you for the Gauss's law, that's something you're supposed to be able to do. I just showed you one. Now I'm going to show you two more really quickly, but I think this might be a good time to take a break. So let's take a break till 6:55. I'll be here in case you have any questions, but you're free to, do whatever. And I'll give you a warning in about a minute till. You can ask questions if you want. I'm sitting here the whole time. All right, got about 1 minute left, everybody. All right, it's time to get started. So I've drawn a solenoid here. So what you can imagine is those top circles are, I'm looking at the end of a wire, sort of like you're looking at the end of the wire. If it's got a dot in the middle, then you're looking at the current coming out of the board or out of the page in this case. And then if it's got the cross, that's like the back of an arrow with the little feathers, that's going into the page. So you can imagine the current coming out and then going down like this and going back in the X immediately below it. And then it goes back behind the screen and comes back up to the next circle out of it. That's what a solenoid is. You can imagine is basically a really neatly wrapped electromagnet like you did in grade school, where you take a wire and wrap it around a nail and then you run current through the wire and that makes the nail magnetic and that sort of thing. Only with this one, we've pulled the nail out, so we just have the solenoid with the wires. Now, what we've said was the radius of this thing is supposed to be R. So what I'm going to also show on this drawing is that from here to here is 2R. And if you look at the individual wire, like this one right here at this end, according to our right-hand rule, if the wire has a current coming out, then the magnetic field is going around counterclockwise. So directly above the wire, it should be pointing to the left. Directly to the left of the wire, it should be pointing down. Directly below the wire, it should be pointing right. And directly to the right of the wire, it should be pointing up. And that's true for all of them. So what we ultimately get is a series of magnetic field lines that go from left to right. And in fact, because of all those different currents, we get a much larger magnetic field in there. So out here, B is approximately 0, and inside, B is strong. So it's a really big magnetic field inside. Now, I need to do the 3-step process. So what I'm going to do is say solution. My hypothesis, if I draw my coordinate system, which I will now, I'm going to say this is the X direction. And I'm going to say, let's say this is the Y direction. Okay. So you can see the X-axis goes all the way through here, basically. That was really bad. Ooh, I hated everything about it. Oops, didn't hate it that much. Okay, so I'm going to take away all that X-axis stuff. It turned out crappy. But the main thing is you see that the X-axis is pointing to the right and the magnetic field is pointing to the right. So my hypothesis is going to be, got to erase one more time. What? One more time. Okay. My hypothesis is going to be that B is equal to B, and it may depend on, for instance, Y, but it's supposed to be very long solenoid. So it should only depend on Y, not on X. And I'm going to say this is pointing in the I hat direction. I'm going to use the integral B dot dl, is equal to mu 0 I enclosed. And I'm also going to use the magnetic flux is equal to the integral of B dot dA, or excuse me, yeah, B dot dA. And I'm going to use that the self-inductance or the inductance is N times phi B over I. I've said this wire has a length script L, has a radius R, has N coils, and I'm going to pretend like it's carrying a current I, but ultimately that current I should not appear in the inductance. Okay. So with all of this, I can now begin. I'm going to start by writing the left-hand side of Ampere's law. So the left-hand side of Ampere's law is the closed integral B dot dL. Now, in order to do that, I need some kind of Amperian loop. So the Amperian loop I'm going to choose is going to be from right here. Then it's going to go all the way, let's say, over to here. And then it's going to come up like this. And like this. And I'm going to integrate because I want the currents coming through the middle to be in the positive direction. I'm going to integrate around it in a counterclockwise direction. Now, this integral is a little more complicated, so let me show you what happens. It becomes, let's start right here. Actually, I wanted to do that in red. Oops, I did not mean to do that. Let's start right here and go that way. So I'm going to say B of y I hat, and then of course going along that, the dl would just be dx I hat, and that's along the bottom. So I'm going to put BOT for meaning the bottom section. And then I'm also going to integrate along the right section. And in that case, you're going to see that you do have B of y I hat, but you also have it's going to be zero sum. And then you have a DL in this case is going to be dy j hat. Now we have to do the top. So I'm going to integrate over the top. Again, in this case, though, the magnetic field is essentially zero. So I'm going to write 0 dotted with negative dx I hat, because that's the line integral to go to the left, or that's the differential line element to go to the left. And then I'm going to say plus the integral over the left side. And this time the magnetic field is going to be 0 for some of it, but it's also going to be B of y I hat for some of it as well, and it'll be dx I hat. Okay. Or excuse me, that one would be dy, negative dy j hat. Sorry about that. So let me put it in parentheses. This one will be negative dy j hat, because I'm going to integrate in the downward direction, and we already said our y direction is up. So that's what breaks down here. So you should be able to make sense of this, that this is 0, this is 0, and this is 0. Notice this first one that I marked as 0 is not 0 because the magnetic field is 0, because there's some parts where the magnetic field wouldn't be 0. But when you do a dot product between I hat and j hat, you get I hat dot j hat is equal to 0. This one's just 0. The one that says top, that's 0 because B is approximately equal to 0 out there. And this one is 0 again because I hat dot j hat is equal to 0. So ultimately, I'm going to call this length, the width of this Gaussian or Amperian loop, I'm going to say the length of this is L1, like that. So my integral the only one that survives is the bottom one, and that's going to be B of Y times L1. So that's the left-hand side of Ampere's law. Any questions on that? The right-hand side is going to be mu 0 times I enclosed. Well, each current is carrying each loop is carrying a current I. So I know it's going to be mu 0 times I, but I need to figure out how many are in a length N1. Well, I can define little n to be big N divided by script L. So that's like our coil density. That's the number of coils per unit length. So if I take that lowercase n and I multiply it times L1, then that'll be the number of wires, and then times I will be the amount of current. So this L times N1 is number of wires in loop, in Amperian loop. So now I can set the left-hand side equal the right-hand side. Left-hand side equals right-hand side gives me B of Y times L1 is equal to mu 0 N times I times L1. So you can see immediately that the L1s cancel out, and I've got that the magnetic field is equal to mu 0 lowercase n times I, and it points in the I hat direction, and this is for inside solenoid, and N is defined to be N over L. So I now have the magnetic field for a solenoid. Now I'm going to finish step one. So step one is done. Now I'm going to do step two. So I have to say phi b is equal to the integral of b dot dA. Now, here's the point. The A that we're going to do is going to be this circular area right here. Okay. And the vector that represents it is going to be pi r squared times I hat. So this is dA is equal to pi r squared I hat. So now I can write this as the integral of mu 0 n times I hat dotted with pi. In this case, the b didn't depend on the r at all. That's why I could just write pi r squared instead of having like a differential and all that stuff. So I'm just going to say pi r squared I hat. Again, the dot product's a linear operator, so I can pull all the constant stuff out in front. I'm going to say mu 0 pi n I r squared integral of, in this case, actually, it's not even the differential area element. It's not even a differential area element. It just should be called A. Sorry about that. Let me write it a little better anyways. I'm going to say A is equal to pi r squared in the I hat direction. Because we don't actually have to do an integral with this one because it doesn't depend on anything. So ultimately what I'm going to do, erase all this, I'm just going to go ahead and say the result is mu 0 n times I times pi r squared. That's the flux. Now I'm going to do step 3. Step 3 requires that I use L is equal to N times phi B over the current. So L is going to be the total number of turns N. And in fact, since lowercase n is N over L, I'm going to write mu 0 pi r squared n squared over, remember the lowercase n was technically big N over L, so I have an L over here, and I didn't write in the I, so the L or the I has already been divided out. So that's the entire formula for the inductance of a solenoid of radius R and total number of turns N. Any questions on that? All right, let me show you another one, and then I got a couple other things to show you, and you'll be ready to roll. No questions on that? So this is just another paradigm you're supposed to be able to do. Now we're going to take and imagine that same solenoid. Imagine it being so long that we can form it into a circle. And let's imagine that I can draw a circle. So we're going to do that over again with this. There's a circle. Now I'm going to attempt to draw a second circle to represent the outer part of the solenoid of the torus. Now, what's really going on here is you can imagine that I have a bunch of wires like this, and all of these wires have currents coming out of the page, and then all of these wires, which should be one correspond to each one over there, has currents going into the page. Yeah, into the page. The other ones were out of the page. Now, that goes around and around this way and this way. Okay. So what I'm going to say for starters is that I'm going to call this radius from, let's say, from the center to here, which is about the midline. I'm going to call that R, but then I'm also going to imagine that it has a cross section right here whose area is A. So remember, it's like a donut. So if you cut the donut in half, you'd see two circles, one here and one here. Those circles have a radius A. Okay, so that's going to come in handy when I go to calculate the inductance. Okay, so I'm going to make my Amperian loop, and I'm going to make it specifically go around in a counterclockwise direction so that it all the inside currents are going in the positive direction according to the right-hand rule. So I'm integrating around this way, and I'm going to start with solution. And again, the key equations I'm going to use is my hypothesis is that B is going to equal, let's say, B of R, and it's going B of big R, I should say. Times theta hat. And I'm also going to say the integral of B dot dl is equal to mu 0 I enclosed. This is going to have n turns. And I'm also going to say that flux is equal to the integral of B dot dA. And I'm going to say that L is equal to N phi B over I. And I'm going to start off with the left-hand side of Ampere's law. So the closed integral B dot dL is going to become the integral of B of R theta hat dotted with R d theta theta hat, which I think you know enough to realize this is just going to be 2 pi R times B of R, just like the other one. Now the right-hand side is going to be mu 0 times I enclosed. That is mu 0 times N, the number of turns, times I, because every one of those currents is in there. So now I can set left-hand side equal to right-hand side. I'm trying to do better about drawing my S's. That means 2 pi R B of R is equal to mu 0 big N times I. Remember, the solenoid had a little n, that's the difference. But notice this is going to look just like the formula for a long straight wire, but it's as if there's n of them. So what we get is B is equal to mu 0 I over 2 pi R and times N, and all that's going to be in the theta hat direction. And that is the magnetic field inside the solenoid. Notice that R is just indicative of the size of the torus. There's no real reason to assume that the magnetic field is going to change that much if you go to the inside edge versus the outside edge, but in principle it could. Okay, so we've now done step 1. Now we do step 2, which is where we calculate that the magnetic flux phi B is equal to the integral of B dot dA. Now, the R doesn't really matter too terribly much. We normally make the distance between the inner radius and the outer radius very, very small. So even if there was a little bit of change in the magnetic field from the inside edge to the outside edge, it wouldn't matter too much if they made it really narrow. So for a really narrow torus, we're going to get that basically the magnetic field is mu 0 N times I, and then the area it goes through is pi A squared. So that's pretty much it. Now I can say step 3 is L is equal to N times the magnetic flux divided by the current. I don't know why I wrote that in red, but anyways, L is going to now be mu 0 N squared I pi A squared. All that's going to be divided by I. So ultimately we can say this is all mu 0 times pi A squared times N squared. And what happened, of course, was that I canceled out, and we're just left with this. So that's the inductance for a torus. So those are the 3 paradigms you should be able to do. It's now 7:18. I actually got quite a bit of time left to do the last little bits. And the last little bits are introducing you to Faraday's law and Lenz's law. Okay. Now that's actually a little more complicated than you'd think, but this is just the parts that I think is important for you guys. So you've got to be able to do this Ampere's law to calculate the magnetic fields for various distributions I'll keep it simple because I haven't had enough time to explain these over to you, but these three versions you should be able to do, okay? Now, Faraday's law says that E is equal to negative N, where N is the number of loops, times d phi b over dt. That's Faraday's law. And what it tells us is whenever you have a changing magnetic flux, that can create an EMF, a voltage. So this quantity is the EMF, which is equal to the voltage. The negative is basically a mathematical requirement. If we ever go to plug this in anywhere, we need to stick that negative in. But if we're asked to calculate what the electromotive force is, we're going to throw that negative away. Okay. But the main thing is that N is if you had a single loop with a magnetic field changing through it or the magnetic flux through it changing, then that changing of the magnetic field is going to induce an electromotive force, which is going to ultimately, of course, create a current. That current is going to try to form itself in a direction that opposes the change in flux. So that's another a statement of why that negative sign is there. The induced current I induced, which could be from, let's write it this way, from E is equal to I induced times R. In other words, you can just change that E to I induced times R if you know the resistance, and that's great. But the induced current is in the direction that creates, okay, I'll just write it this way, creates a magnetic field to oppose the change in magnetic flux. Okay. This is called Lenz's law. And it also refers to the negative sign there. It turns out that if the induced current went the other way, that would actually violate the second law of thermodynamics. It basically makes like a perpetual motion machine. So that can't be done. This is a very important concept, being able to guess the direction of an induced current. So let me show you some quick examples. We already taught you that the magnetic field is like what I said was like seniors, in that they generally leave the north and enter the south. So if I had a bar magnet some distance away from a loop of wire, okay, and the magnetic field, of course, from this is going to go like this. And like this, and I'm trying to draw it where it doesn't actually hit the wire loop because I'm trying to pretend it's far enough away from the wire loop where it's not having any major effect. But what I'm going to do is I'm going to push the magnet up towards that loop and then show you what the induced current direction is. So when this magnet is really far away, there's no magnetic field going through the loop, so the flux is zero. But as you bring it closer and closer, it's going to create a magnetic field, and that magnetic field is going to be pointing up through the middle. So what's going to happen is we go from a case where there's no flux to a case where there's a flux with a magnetic field pointing up. The laws of physics tell us that an induced current is going to happen, and that current is going to try to create a magnetic field that opposes the change in flux. Well, the flux was going from zero to something, so it's going to try to fight it back to zero. So it's going to try to create a magnetic field pointing in the opposite direction. So the induced current will be made to create a B field pointing down. Okay, that's because there was no magnetic field. Now there is one and it's going up. I'm going to try to fight that by creating a magnetic field going down. So if I do that, if I actually create a magnetic field going down, the current in the front part of the wire has to be positive, has to be to the left because, or excuse me, yeah, because if you grab that front wire with your thumb, with your middle fingers going down through the middle, then you see your right thumb points to the left. So the induced current is going to be clockwise as seen from above. Front implies left. Back, the back wire, implies right. Okay. So that's how Lenz's law works. And your book gives a ton of examples in there in the opening chapter, but it also gives a ton of examples. I mean, in the chapter, but it also gives a ton of examples in the actual attempts to try the problems in the end of the chapter. That's what I was going for. I don't know why I did all that. But anyways, you get a lot of different examples. If you imagine now, for instance, the same magnetic field or the same magnet, let's imagine now it's starting to leave. It's starting to leave the loop so that now we have, just looking at the tail end of it, we have the south end of the magnetic field going this way, and then the loop going that way, and the magnet's going that way. What's happening is the magnetic field inside the loop is decreasing. So this time it's going to try to build up the magnetic field. The magnetic field is pointing up through the middle, so it's going to try to make it stronger because it's actually getting weaker. So again, I'm going to take my right hand and stick my fingers up through the middle of that black loop, and then I can grab the front wire with my palm and see that my right thumb is now pointing to the right. So in this case, it's actually going to be counterclockwise. Okay, so that's what Lenz's law is all about. The big thing about this is I want you to be able to use this equation so we can look at a problem. And this is sort of the classic problem, so it's going to be repeated over and over and over again. What I'm going to do is I'm going to say there is a green magnetic field. So there's a green magnetic field that is uniform and really big. And it's obviously pointing into the page. That's why I'm drawing X's instead of dots. I didn't draw the actual circle around it, but you really don't need those, to be honest with you. Your book hardly ever uses them. I almost always use them. But what we're going to imagine is that the magnetic field abruptly ends right here. Now what I'm going to do is I am going to take a loop of metal going right across here like this. It's going to be a square loop. And let's say it is moving with a velocity v. Okay. I'm going to say the width of this loop is L, and the height of this loop is also L. Okay. Now, as I pull it, what I need to know is the flux. So what I'm going to ask for is, what is the induced current? Okay. I'm going to say the total resistance is R. So that's what I'm saying that is. And what I'm going to say is the initial flux. Let's actually put this as a solution. So I'm going to get rid of that. Okay. So that's what I'm going to use. Now, what I'm going to say is the initial flux, phi 0, which means phi at t equals 0, is going to be B, the strength of the magnetic field, times L squared. Because you see the entire magnetic, or the entire loop is completely submerged in a magnetic field. But as this thing moves, like when the loop has moved over to this far, then it's going to be hanging out. And in fact, this side is still L, but this side in the magnetic field, mind you, this side is not L. Actually, yeah, that's cool. This side, in fact, it was L, but now it's L minus V times T after T seconds elapsed. Does that make sense? So we can say that the area as a function of time is equal to L times L minus VT. That implies that the flux, the flux as a function of time is B L times L minus VT. And of course, that implies that dB over dt is equal to d by dt of b L squared minus b times L times v times t. And clearly that's just negative b times L times v. That implies the induced EMF is negative N, which is 1, because there's only one loop here, times negative BLV. And since they're both negative, that's why I kept the negative in there, because it automatically just cancel out and give it to me. So I'm going to say that E is actually going to be equal to BLV. That's an important result because your book is going to ask you all sorts of crazy things like, what if an airplane has a length of, 60 meters and is moving at 740 meters per second through the part of the Earth's magnetic field that points straight down? What's the voltage developed across the end of the wings? Well, you're just going to blindly apply B times L times V, where L is the length of the wave, or the length of the wings from tip to tip. B is the strength of the magnetic field of the Earth, which is normally about half a Gauss, or 0.5 times 10 to the negative fourth Tesla. And then V is the velocity of the plane. And you can put all that in and it'll tell you, and your book even does an example. It gets roughly a volt, so it's not a huge amount, but that's important. We'll use that. Now, in addition to that, we can also use E is equal to I times R, and that's I induced, of course, times R. So we can also say that I induced would be uh, basically the E divided by R. So that's going to become BLV over R. So that's another important equation that you'll use over and over again. And in fact, if you had, instead of a single loop of wire, if you had N loops of wire, then you could get a result like E is equal to NBLV, or you could get I induced is equal to NBLV over R. So that's a typical setup of what you've got to be able to do. So those equations just come in super handy. You do need to do them, that sort of thing. But that's about it. Let me see if I'm trying to think if there's anything else really jumping out at me. Oh, yeah. So from that same equation, where we said N is equal to, or E is equal to negative N d phi dt, we get a transformer equation. Okay. So your book talks about this too, but let's imagine a scenario. I'm just going to show you how to solve it. So let's imagine for a second we have a big chunk of iron. And I usually tell my students this is like the belt buckle that kids wore when you did a play for Thanksgiving. So the pilgrims, of course, always looked like they had a big old belt buckle on. Don't know why. At least that's the way it was in my childhood. So we're going to imagine a pilgrim belt buckle made out of iron. And that's really good. That is the material of choice. What we found over the years is it's better to take several little thin slices of iron and glue them together, and that prevents some eddy currents that can steal energy from it. But the neat thing is we're going to take a wire now, and this wire is going to come in and then loop around like so. And then come out like here, come out here, and I'm going to call this VN. That's the voltage that's in, and I'm going to say that a current I in was going through there. This, as I said, is a transformer. It's not more than meets the eye. It's a different transformer. Okay, now coming out of it is going to be another wire. And I'm going to say this one has N1 turns. This one over here has N2 turns. And in fact, this voltage is V out. And the current would be I out. Now, the transformer equation that's relevant here is basically what you can think is, well, that way works, but I don't necessarily want to do that. What I'm going to say is Vn times N1 is equal to N2 times V out. Like that. So that you could say V out is equal to N1 over N. Nope, that's wrong. Hold on, let me double check real quick. V out should be, yes. Yeah, I had that backwards. Sorry about that. So what equation we have is going to be V1 over N1 is equal to Vn over N1 is going to be equal to V out over N2. And now we can say that V out is going to be N2 over N1 times Vn. That's a very important equation. That's the transformer equation. And if N2 is greater than N1, then it is a step up transformer. In other words, the word up and down when you're talking about a transformer deals with the voltage, not with the current. And additionally, since P in at best is P out, that means that I in times V in is equal to I out times V out. And from that, you can get that I out is equal to N1 over N2 times I in. So this is another important equation. So now let's imagine that I have a specific problem we're working. And let's say this wire comes in and has 1,000 turns and has a voltage of 120 volts and a current of 200,000 amps. So this might be, for instance, the power coming from a power creation place, like a coal-fired power plant, turbine power plant, and it's going to serve 1,000 houses, because in general, a homeowner house runs on 200 amps. Now over here, oops, I went a different color on that. Over here is going to be 2 million turns. And what I want to know is V out equals question mark and I out equals question mark. So what I can tell you is that V out is going to be equal to 2 million over, actually I should have said 1 million, but that's close enough. Over 1,000 times 120 volts. So this is going to be 2,000 times larger, and 2,000 times larger than 120 is 2,400 volts. Let's double check that math. So I'm going to do 1,000. Oh, it should be 24,000. Sorry about that. Left off a number. So it's 240 times 1,000. Oh, that's 240,000. My fault. Oops. Sorry about that. I was thinking about the time and I got sort of discombobulated here. So this turns out to be 240,000 volts, which is not unlike the power that you see on those really tall poles out in the country that look like a human with no arms and head. They do, in fact, specifically send them out at, on the order of a couple 100,000 or even 1,000,000 volts. The current, on the other hand, watch what happens with that. I out is going to be 1,000 over 200 or 2,000,000 and times 200,000 amps. So this one's actually going to divide it by 2,000. So I'm going to get that it comes out as 100 amps. And that's exactly why they do this, is because P is equal to I squared R is the actual power dissipated. So when I go from 200,000 amps to 100 amps, I save a butt ton of money because it literally is 200,000 squared versus 100 squared. So there's an example for you. These should be all the types of problems that you run into. All we've lacked is by skipping chapter 30, 31, which we haven't done. This actually included chapter 30. We've missed some of basically Maxwell's equations, but that's okay. We've done all of the equations. I will tell you that really what they are is Gauss's law, which is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Then we can say there's actually a equivalent of Gauss's law for magnetic fields, but that's equal to 0. And that is the proof that there's no monopoles. So for instance, when you cut a magnet in half, you don't get a north pole and a south pole. You get two magnets with each of which have a north pole and a south pole. And these come from del dot E equals rho over epsilon naught, and del dot B is equal to 0. That's the differential form of these equations. You can transform them back and forth using Stokes' theorem and Green's theorem, that kind of thing. There's also another one that says the closed integral of E dot dL is equal to negative n d phi b over dt, and that's Faraday's law. And then there's another one, the closed integral of b dot dl is equal to mu 0 I enclosed, and this is Ampere's law, but Maxwell has to fix it because of that little bubble thing I told you about. Any surface that has a boundary as that little Amperian loop, any surface will do. Well, if you take and wrap that Amperian loop around the wire, but then you let the surface that is bounded by that bounds it go in between the plates of a parallel plate capacitor, then no current's going through that whatsoever. So Maxwell figured out that you actually have to add a mu 0 epsilon 0 times the partial derivative of the electric flux with respect to time. So that makes corrected Ampere's law. With Maxwell's correction. So feel free to read all that in chapter 30 and 31, mostly 31, but that's basically it. With those four equations, we can ultimately solve almost all problems in electricity and magnetism until we get to the microscopic level. And in fact, we normally use them in the differential form, which I haven't given you here, but your book does in the appendix. So you guys are free to go. Thank you for coming, both of you. I appreciate it. Feel free to send me any messages if you have any problems, but definitely start working on taking your tests and all those practice tests, and I'll get you up a final that's more geared to show you what 27, 28, 29, and 30 are required of you. Okay. The homeworks, again, technically I'm only going to require you to do 17 through I said 30, but I'm gonna go ahead and say 17 through 29. But notice we did cover a little bit of 30 here. So those are the homeworks that are required. All the other ones, other than chapters 17 through 29, are going to be counted as extra credit. And what's most important is that you guys do really well in the final. That can erase everything. So thanks for coming. This video should be posted later tonight, as well as these notes. Let me know if you have any questions, and I'll wait here for the last person to leave in case anybody has any questions. Yes, I just saw somebody post something. Let me check what that was. Oh, yes, Teamer, go for it. You can type it or say it, whatever you want. Does your microphone work, Teamer? Oh, they got it. Oh, gotcha. Let me check that real quick. I think I remembered seeing it and I was going to reply tonight. Let me see. Oh, there, I got you. Okay, check that too. See your email too now. Ah, yes, that has been, hold on a second. Let me go to a chat room so we can discuss this. I'm going to go ahead and stop recording too. Did you have a question, Ethan?
Yeah, my question was if the Ampere's law, Faraday's laws are going to be on the final similar to the Gauss's law problem we had.
Yes, that was the whole point of me making sure I covered those three for you. You should be able to do any of those three that I derived for you, as well as solve the transformer equation, as well as use Faraday's law, that especially in that form, E or IR is equal to negative N d phi dt.
And those will all be on the practice final.
Yeah, and they're already in there on the practice versions that I have, but they might be a little tougher than is really required for the final. So, like I said, I'm trying to make up a more accurate version of the practice final. And when I have that, I'll email you.
All right, thank you.
You're welcome.
Can you
Okay.
hear me, Professor?
Yeah, I got you.
All
And
right.
I've now, as far as I can tell, I stopped the recording, so you're not on there.
Nah, I'm not worried about that anyways. So, like the other guys in the class, they let me know that that they had asked you about the lab reports, and that you had said that like if you don't turn 4 of them in, that you will be given a failing grade. And I'll
That
be honest, I've been very lazy with the lab reports
Gotcha.
because like I figured the rest of my grade would be good, and I'm transferring it to Virginia Tech anyways, so.
Right. Yeah, that is the way I've been interpreting that. But technically speaking, I guess you've got me in a loophole because I didn't say that, but I said missing 4 labs. I generally say missing 4 labs is missing 4 lab reports, but I won't.
Okay.
I would prefer you to try to get them in.
Yeah, I've been working
Not
on
done
them.
that well.
Okay. Yeah, and like I mean like if you want to work on a compromise where like you just give me a 0 for labs too, I'm cool with that. Like,
Yeah, I'm definitely not going to give you an F for the grade. Don't worry about that.
okay.
That's
Thank you.
definitely a loophole. And
Yeah.
not only that, I had a couple of students that actually had some problems where they had to miss even 4 days. So I
Mhm.
gave them a special pardon. So I'm certainly going to give you one. So get as
Okay,
much as
thank
you
you.
can done so I can give you a good grade. But yeah, if you don't have one turned in, I'm gonna have to mark it as a 0. But
Yeah,
that's
yeah.
still your grade.
Yeah, yeah, like I'm not too worried about that, especially with like how the practice will like because like the practice exams will also add like to your final grade.
Mhm.
Then you also lowered it to be a 68.5, I think, for a C,
Right.
is what's in the syllabus.
Yeah, I
And
think
like
it's
for
68
transfer, you
and a
just need
half.
a C, I
Yeah.
believe,
Yeah.
for transfer credits. So
Yeah. I think you'll be fine.
okay.
With
I just
that.
want to make sure, because like I'm taking this class so that I can graduate a year early,
Right.
so like I just want to make sure with you.
Yeah, you're good. Don't worry about it, bud.
Okay, thank you. I
All
really
right.
appreciate it. I know I'll see you on Monday, but you've been a really cool professor anyways. Thank
Thank
you.
you. I
Yeah.
appreciate it. You guys have been great. I liked having you during the summer, and drop me an email sometime.
Yep. Thank you.
All right. See you, bud. Bye
Yep.
bye.
See you.